It is a universal experience, the most fundamental sensation of our existence. We feel it in the steady beat of our hearts, in the turning of the seasons, and in the lines that map the stories upon our faces. It is the river that carries us from birth to death, a current so powerful and so persistent that we rarely stop to question its direction. But what if we did? Imagine a cup slipping from your grasp. It falls, it shatters into 100 pieces on the floor. You can rewind a film of this moment and watch the shards miraculously leap from the ground, reassembling themselves perfectly into your hand. But you will never witness this in reality. You will never see the spilled milk gather itself from the table, or the smoke from an extinguished candle funnel back into the wick. Our experience screams at us that this current, this flow we call time, is a one-way street. The past is a fixed landscape of memory, the future an undiscovered country of possibility, and the bridge between them, the present, moves in only one direction, from yesterday towards tomorrow. This is the arrow of time, but in the pristine, elegant mathematics that describe our universe, this arrow is strangely absent. The fundamental laws of physics, from the grand cosmic dance of galaxies to the frantic waltz of subatomic particles, seem to work just as well backwards as they do forwards. They are symmetric in time. So where does this profound asymmetry, this relentless, irreversible march into the future, come from? Why does the cosmos forbid us from turning back the clock? The answer is not found in a single law, but is woven into the very fabric of existence, from the birth of the universe to its ultimate, distant fate. It is a story of order, chaos, and the profound power of probability. For centuries, our conception of temporality was simple, almost intuitive. The ancient Greeks, like the philosopher Heraclitus, saw existence as an ever-flowing river. No man ever steps in the same river twice, he mused, for it's not the same river, and he's not the same man. Time was change, a perpetual state of becoming. This poetic idea was given a rigorous, mathematical foundation by the titan of classical physics, Sir Isaac Newton. In Newton's universe, time was absolute. It was a grand, cosmic metronome, ticking at a constant, unwavering rate for every observer, everywhere in the cosmos. It flowed equably without relation to anything external. This absolute chronology was the backdrop against which the drama of the universe played out. The planets moved in their predictable orbits, projectiles arced through the air with mathematical certainty. The universe was a magnificent clockwork mechanism, set in motion by a divine clockmaker. And in this deterministic world, if you knew the precise position and momentum of every particle at one instant, you could, in principle, calculate the entire future and reconstruct the entire past. The equations governing this clockwork cosmos were time-symmetric. Running them backwards simply described the same events in reverse. There was no inherent direction, no built-in arrow. The shattering cup and the reassembling cup were equally valid solutions. Yet, this perfect, reversible clockwork model could not explain the most obvious feature of our world, the irreversible reality of decay, of aging, of things falling apart. The answer would not come from the pristine orbits of the heavens, but from the grime, smoke, and thunder of the Industrial Revolution. The 19th century was an age of steam and steel. Engineers were building powerful machines to drive factories and locomotives, and in their quest for greater efficiency, they stumbled upon a new, fundamental truth about the universe. They were developing a new science, thermodynamics, the study of heat and energy. They discovered that energy could be converted from one form to another, but never created or destroyed. This was the first law. But they also discovered a more subtle and far more profound second law. Every time energy changes form when coal burns to produce steam, or steam pushes a piston, some of it is inevitably lost as waste heat. It dissipates into the environment, becoming unusable. You can't gather all that dispersed heat and use it to reconstitute the original lump of coal. The process is irreversible. This simple observation about the inefficiency of steam engines held the key to the arrow of time. In the 1850s, the German physicist Rudolf Clausius formalized this idea with a new, mysterious quantity he called entropy. Entropy, in essence, was a measure of the disorder or randomness of a system. The second law of thermodynamics states that in any isolated system, the total entropy, the total amount of disorder, will always increase or, at best, stay the same. It can never decrease. The universe, as a whole, is moving from a state of order to one of disorder. This law explains why a hot cup of coffee cools down. The ordered state is having all the fast-moving, high-energy molecules concentrated in the cup. The disordered state is having that energy spread out evenly throughout the room. Energy naturally flows from hot to cold, from order to disorder, increasing the total entropy of the room. It explains why buildings crumble, why organisms decay, and why memories fade. The arrow of time, it seemed, was the arrow of increasing entropy. The universe has a clear and unambiguous direction. It is a one-way slide into chaos. But this raised an even deeper question. Why? Why should the universe favor disorder over order? The answer would come from one of the most brilliant and tragic minds in physics, an Austrian genius named Ludwig Boltzmann. Boltzmann was not content with merely stating that entropy increases. He wanted to understand why times it increases. He proposed a radical idea. He imagined that all matter was composed of countless tiny atoms, colliding and jostling according to the simple, time-symmetric laws of mechanics. From this microscopic, mechanical world, he sought to derive the irreversible second law of thermodynamics. Boltzmann's great insight was that entropy is not a fundamental force, but a matter of statistics and probability. Disordered states are simply vastly more probable than ordered states. To grasp this, consider an analogy. Imagine a brand new deck of cards arranged in perfect sequence, ace to king for all four suits. This is a state of very low entropy, a state of perfect order. There is only one way for the cards to be in this specific sequence. Now, shuffle the deck. The cards become jumbled. This is a high entropy state, a state of disorder. What are the odds that if you keep shuffling, the cards will spontaneously return to their original, perfect sequence? The number of possible ways to arrange 52 cards is an astronomical figure, roughly 8 followed by 67 zeros. It is a number far greater than the number of atoms in our galaxy. There is only one perfectly ordered arrangement, but there are countless trillions upon trillions of disordered arrangements. Every shuffle lands you in one of these overwhelmingly numerous disordered states. It is not physically impossible for the cards to fall back into perfect order, but it is so statistically improbable that you would have to shuffle for trillions of years, longer than the current age of the universe, to have even a remote chance of seeing it happen. Boltzmann argued that this is precisely what happens with the atoms in the universe. There are vastly more ways for atoms to be arranged in a disordered, high-entropy configuration than in an ordered, low-entropy one. The universe isn't being pushed towards disorder by some mysterious force. It is simply evolving, through the random collisions of its constituent parts, from an incredibly unlikely state of low entropy into an overwhelmingly more probable state of high entropy. The arrow of time is the universe's journey from the improbable to the probable. The shattering of the cup is a journey from a single, ordered arrangement of atoms into one of the countless trillions of disordered arrangements of shards. The reverse is statistically forbidden. Boltzmann's ideas were revolutionary, but they were met with fierce resistance. Many of his contemporaries in the scientific establishment refused to believe in the existence of atoms, let alone his statistical interpretation of reality. They pointed to the time-symmetric nature of the underlying mechanics and argued that for every process moving towards disorder, a reverse process should be equally possible. Tormented by this scientific rejection and his own failing health, Ludwig Boltzmann took his own life in 1906, never living to see his atomic theory and statistical mechanics become the cornerstones of modern physics. His tombstone is etched with his great equation, S equals K log W, forever linking entropy S to probability W. It is a tragic and profound epitaph for the man who explained time's arrow. Boltzmann's statistical explanation provides a powerful reason for why time flows one way, but it hinges on one enormous, universe-sized assumption. It requires that the universe began in a state of extraordinarily low entropy. Like our deck of cards, the cosmos must have started in a state of near-perfect order. But just as this explanation was taking hold, another revolution was brewing, one that would completely transform our understanding of space and time itself. The young Albert Einstein, working as a patent clerk in Bern, Switzerland, was about to shatter Newton's clockwork universe forever. In 1905, Einstein published his theory of special relativity. Its consequences were mind-bending. He demonstrated that there is no absolute time, no universal cosmic metronome. The rate at which time passes is relative. It depends on your motion. For an astronaut traveling near the speed of light, time would slow down dramatically compared to an observer on Earth. This time dilation is not a trick of perception, it is a real, physical effect. Clocks aboard fast-moving GPS satellites must be constantly corrected. To account for this relativistic slowing, or their navigation systems would fail within minutes. 10 years later, with his general theory of relativity, Einstein went even further. He showed that space and time are not separate entities, but are woven together into a single, four-dimensional fabric, space-time. Massive objects like stars and planets warp and curve this fabric, and this curvature is what we experience as gravity. The Earth is not being pulled by the Sun, it is following the straightest possible path through the curved space-time created by the Sunday. This new picture of reality has staggering implications for the nature of time. If space and time are part of a single continuum, then time is much more like a spatial dimension. This leads to a model of the universe known as the block universe, or eternalism. Imagine a loaf of bread. Each slice of the loaf represents the state of the universe at a particular moment. The first slice is the Big Bang, the last slice is the ultimate future, and all of history is laid out in between. In this view, the past, present, and future all exist simultaneously. They are all equally real. The Big Bang is not an event that times happened times and is now gone. It is a location in space-time, just as your birthplace is a location in space. The future is not an unwritten realm of possibility. It is already there, a fixed landscape further down the block of space-time. Our sense of the flow of time in this model is an illusion. Our consciousness simply moves along the time dimension of this block, experiencing one slice after another, creating the sensation of a moving present. The distinction between past, present, and future is merely a stubborn, persistent illusion of human perception. But if the entire history of the universe is a static, unchanging block, where does the arrow of time, the sense of direction, come from? Even within this static block, there is still a clear structure. The slices are arranged in a specific order, an order dictated by entropy. The slice corresponding to the Big Bang has incredibly low entropy. Slices corresponding to the distant future have incredibly high entropy. So while the block universe does away with the flow of time, it preserves the arrow of time as a fundamental asymmetry. Built into the structure of space-time itself, the universe is ordered in one direction and disordered in the other. Our consciousness, our lives, our very psychological experience of time is oriented to perceive this direction of increasing entropy. We remember the past, the lower entropy state, and we anticipate the future, the higher entropy state. Einstein's relativity provided a new stage for the cosmic drama, but Boltzmann's statistical law remained the star of the show. The arrow of time was still the arrow of increasing disorder. However, as physicists began to explore the universe at its smallest scales, they discovered a new realm where the rules of reality seemed to defy all classical intuition. The world of quantum mechanics presented a new and baffling paradox. At the subatomic level, The world is a storm of probabilities and uncertainties. Particles can be in multiple places at once, they can tunnel through impenetrable barriers, and they can be mysteriously linked across vast distances. Yet, for all this strangeness, the fundamental equations that govern this realm, like Schrödinger's equation, share a key feature with Newton's laws. They are perfectly time-symmetric. A film of two electrons colliding and scattering looks perfectly plausible, whether you play it forwards or backwards. There is no inherent arrow of time in the basic interactions of matter. This creates a profound disconnect. How can a macroscopic world, which is built from these quantum components, exhibit such a powerful, irreversible arrow of time when its fundamental constituents operate by reversible rules? It's like building a one-way street out of cars that can drive equally well in either direction. One of the deepest mysteries in quantum physics, the measurement problem, may offer a clue. In the quantum world, a particle exists in a cloud of possibilities, a superposition of all its potential states, described by a wave function. But the moment we try to measure it to observe its position, for example, this cloud of possibilities inexplicably collapses into a single, definite outcome. This act of measurement, this interaction between the quantum system and the large-scale classical world, seems to be an inherently irreversible process. You can't unmeasure a particle and restore its original cloud of possibilities. Some physicists believe that this process of wave function collapse is where irreversibility, and thus the arrow of time, first enters the physical world. It is the bridge between the ghostly, time-symmetric quantum realm and the solid, time-asymmetric reality we experience. Another idea, known as quantum decoherence, suggests that the arrow of time emerges from the way a quantum system interacts and becomes entangled with its vast environment. A single, isolated quantum system can maintain its time-reversible behavior, but as soon as it interacts with the billions upon billions of particles in its surroundings, information about its initial state leaks out and becomes hopelessly scrambled throughout the environment. Trying to reverse the process would require tracking and reversing the state of every single particle in that environment, a task of impossible complexity. In this view, irreversibility is an emergent property born from the sheer complexity of the macroscopic world. The quantum realm adds layers of immense complexity and mystery, but ultimately, all roads lead back to one monumental question. Whether we are talking about Boltzmann's statistics, Einstein's spacetime, or the mysteries of quantum collapse, every explanation for the arrow of time relies on a single starting condition: that the universe began in a state of extraordinarily low entropy, a state of unbelievable order. This is what cosmologists call the past hypothesis. The arrow of time is not a law of physics in itself, but rather a consequence of the specific initial conditions of our cosmos. Our universe didn't just happen to start, it started in a very, very special way. All the evidence we have points to a beginning, some 13.8 billion years ago, in an event we call the Big Bang. At this moment, the entire observable universe, all the matter and energy that would eventually form trillions of galaxies, was compressed into a space smaller than an atom. It was a state of unimaginable density and temperature, but also, paradoxically, of incredibly low entropy. How can a hot, dense fireball be considered ordered? The key is gravity. In the early universe, matter was spread out almost perfectly smoothly. This smooth distribution was a state of low gravitational entropy. Gravity is an attractive force. It pulls things together. Over cosmic time, it has pulled that smooth gas into dense clumps, forming stars, galaxies, and black holes. This clumpy, structured universe we see today is actually in a state of much higher gravitational entropy than the smooth, primordial fireball of the Big Bang. The Big Bang was the cosmic equivalent of a perfectly assembled, unshuffled deck of cards. The entire subsequent history of the universe, the formation of structures, the burning of stars, the evolution of life, has been the process of this cosmic deck being shuffled, relentlessly increasing the total entropy. So, the ultimate question of why time flows forward becomes the question of why the universe began in such a special, low-entropy state. And on this question, physics currently has no definitive answer. It is perhaps the greatest mystery in all of science. Why wasn't the universe born into a state of maximum entropy, a chaotic equilibrium? Why did it start with this immense potential for interesting things to happen? Some physicists speculate that our Big Bang might be just one event in a much larger multiverse, and that we simply find ourselves in one of the rare, ordered pockets capable of supporting life. Others propose models of a cyclical universe where our cosmos could have emerged from the collapse of a previous one. But for now, the low-entropy beginning of our universe remains an unexplained, brute fact, the ultimate source of every broken cup, every memory, and every tick of the clock. This cosmic story, which begins in primordial order, also points towards an ultimate destiny. If the arrow of time is driven by the inexorable rise of entropy, what happens when entropy can rise no further? The second law of thermodynamics paints a stark, desolate picture of the universe's far future. Trillions of years from now, all the stars will have burned out. The galaxies will be populated by the cold, dead remnants, black dwarfs, neutron stars, and wandering planets. Over even more immense timescales, quantum effects will cause even these remnants to decay. Black holes themselves will eventually evaporate through a process known as Hawking radiation. Eventually, after a span of time so vast it defies human comprehension, the universe will approach a state of maximum entropy. It will be a thin, uniform soup of elementary particles and low-energy radiation drifting aimlessly through an ever-expanding, near-empty space. This is the heat death of the universe. In this final equilibrium state, there will be no temperature differences, no structure, no available energy to drive any process. Nothing will happen. And if nothing happens, if there is no change, does time itself still have meaning? In a universe of maximum disorder, the arrow of time would cease to exist. There would be no distinction between past and future. Chronology itself might dissolve into a timeless, featureless void. It is a sobering, and perhaps terrifying, vision of ultimate stillness and silence. So we are left with a profound and beautiful portrait of our existence. We live in a fleeting, precious epoch of the universe's history, a period between the fiery order of its birth and the icy chaos of its death. The arrow of time, this one-way flow that we find so intuitive, is a consequence of that special beginning. It is the unwinding of the cosmic spring that was coiled at the Big Bang. It is the sound of the universe shuffling its cards, moving from its most improbable state to its most probable one. This cosmic arrow provides the direction for everything we know and experience. It allows for the formation of complex structures like stars and planets. It allows for the process of evolution, the gradual accumulation of information that creates life. It allows for the mechanisms of memory in our brains, the laying down of ordered neural traces of past events. Our very consciousness, our sense of self, journeying through a sequence of moments, is intrinsically tied to this thermodynamic flow. We are creatures of entropy. We are born, we live, we age, and we die, all surfing this relentless cosmic wave of increasing disorder. The refusal of time to flow backward is not a minor inconvenience. It is the fundamental rule that makes the universe interesting. It is the reason there is a difference between cause and effect, between a memory and a dream. It is the canvas upon which the entire story of the cosmos is painted. While we may never be able to mend the shattered cup or turn back the clock of our own lives, we can find a deep sense of wonder in understanding why. We are witnesses to a universe in the process of becoming, a universe unfolding from a beginning of exquisite order, powered by the inexorable march of time's arrow on its grand, one-way journey into the endless future. Every photograph you have ever seen captures a moment that is already gone, a ghost of light travelling from a subject to your eyes carrying a story that is by the time it reaches you history. This is true for a portrait of a loved one taken a second ago. It is true for the light of the sun which left its surface 8 minutes before warming your face, and it is profoundly true for the light from the distant stars ancient travellers on journeys of millions or even billions of years. You see, when we build telescopes, we are not just building instruments to see farther into space, we are building time machines to peer deeper into the past. With every lens we polish, with every mirror we cast, we are pushing back the darkness, striving to witness our own cosmic genesis, to capture the ultimate photograph, a portrait of the universe in its infancy. For decades we believed we had found it. The most ancient, most profound, most complete picture of our universe ever taken. It isn't a snapshot of a single star or a majestic galaxy. Instead, it is everywhere you look, in every direction, filling all of space. A faint, ethereal and astonishingly uniform glow of microwave radiation, a whisper of energy just a few degrees above absolute zero. We call it the cosmic microwave background, the CMB, and it is nothing less than the echo of the Big Bang itself, the afterglow of creation. This is not light from a star. It is the light of the universe itself released in a single, universe-spanning flash of freedom. To understand this celestial masterpiece, you must imagine a time long ago, a time before the first star ever ignited, before the first galaxy coalesced from the void. For its first 380,000 years, the entire cosmos was a place of unimaginable violence and pressure, a seething, opaque inferno of fundamental particles. It was a plasma, a chaotic soup of protons and electrons churning in a furnace of photons, the very particles of light. In this primordial chaos, light could not travel. A photon would be born only to be immediately absorbed by a free electron. It would be instantly re-emitted, but in a random direction, only to slam into another electron a fraction of a nanosecond later. Light was a prisoner trapped in an endless, frantic pinball game within the plasma fog. The universe was a star, but we were living inside it. And just as you cannot see into the fiery core of our own sun, you could not see through the incandescent plasma of the early cosmos. There was light everywhere, but there was no sight. The universe was blind. Then something miraculous happened. After 380 millennia of relentless expansion, the universe had grown larger, and in doing so it had cooled. It crossed a critical threshold, a tipping point in cosmic history. The temperature dropped just enough for the frantic dance to slow. For the first time, the protons and electrons, once sworn enemies in a sea of energy, could embrace each other, bound by the electromagnetic force. They formed the first stable neutral atoms of hydrogen and helium. Suddenly, for the countless photons ricocheting through the plasma, the universe transformed. The fog lifted. The electrons that had once been their captors were now locked away inside atoms. The cosmic pinball machine was cleared, the obstacles vanished. And in that instant, all at once, across the entire expanse of reality, light was set free. The photons that had been trapped for eons were released unleashed to travel in straight lines, unimpeded across the cosmos forever. This was the moment of last scattering. The moment the universe became transparent. The moment it could finally see. That ancient light released 13.8 billion years ago is what we detect today as the CMB. Stretched by the expansion of space over its immense journey, its brilliant high-energy gamma rays have cooled and lengthened into the faint microwaves that our sensitive radio telescopes now capture from every conceivable direction in the sky. When we map this radiation, we are looking at the surface of that primordial fireball. We are gazing upon a wall of light that marks the edge of the visible universe, not in space, but in time. It is our definitive baby picture, a snapshot of the cosmos at 380,000 years of age, and its details are breathtaking. The subtle, almost imperceptible variations in its temperature, tiny ripples of 1 part in 100,000, are the seeds from which all future structure would grow. These minuscule fluctuations in density were the gravitational anchors around which the very first stars and galaxies would later form. Every celestial body, every star cluster, every supercluster, every void, and indeed our own Milky Way galaxy, you and I can trace our lineage back to one of these faint smudges on the canvas of the cosmic microwave background. It is the Rosetta Stone of cosmology, a treasure map of cosmic evolution. It tells us the age of the universe, its composition, its geometry. Its discovery confirmed the Big Bang theory beyond any reasonable doubt and ushered in the era of precision cosmology. We thought with this image we had finally reached the beginning, but we were wrong. This magnificent portrait, as ancient and informative as it is not the dawn of time. It is a photograph taken at sunrise, yes, but it tells us nothing of the night that came before. Those first 380,000 years, the true infancy of our universe, remain locked away, hidden from our sight behind that impenetrable wall of light. It is a golden curtain drawn across the stage of creation, and our most powerful telescopes, our most brilliant instruments, can't peek behind it. We can model what we think that era was like. We can write equations describing the physics of that primordial furnace, but we cannot see it. We have no direct observational evidence, no photograph, no fossil. The very light that would carry the story of that epoch was itself trapped by the conditions of the epoch. It's a perfect cosmic paradox. The most crucial moments in our universe's history, the instant of the Big Bang, the mysterious period of cosmic inflation that supposedly happened a trillionth of a trillionth of a trillionth of a second later, the great war between matter and antimatter that decided our very existence, all of these events are lost to us, shrouded in the fog of that early plasma. For decades, this has been the fundamental limit of observational cosmology, the ultimate boundary. To ask what came before the CMB was to enter the realm of pure theory of speculation. It was to ask a question that science, it seemed, could never answer. What if, however, there was another way? What if there was a witness to that earlier hidden era? A messenger that could walk straight through that wall of fire unscathed and unhindered to bring us the tale of the universe's first moments. To find this messenger, we must turn our attention away from light, away from the familiar forces that shape our everyday world, and toward the most elusive, most enigmatic particle in the entire cosmic zoo. A particle so antisocial, so pathologically shy, it can travel through a light year of solid lead without ever noticing it is there. It is a ghost, a whisper, a phantom flitting through the very fabric of reality. It is the neutrino. Your body right now, as you sit here, is being pierced by 100 trillion of them every single second. They are pouring out of the nuclear furnace of the sun, erupting from supernovae and distant galaxies, and streaming toward you from every direction in the cosmos. They pass through the Earth as if it were empty space. They pass through your bones, your muscles, your brain, leaving no trace, no whisper of their passage. They have almost no mass. They have no electric charge. They interact with other matter only through the weak nuclear force, a force so astonishingly feeble and short-ranged that a neutrino can traverse the entire universe and interact with absolutely nothing at all. For most of scientific history, the neutrino was a theoretical necessity, a ghost particle, invented simply to make the equations of nuclear decay balance. Detecting them was considered a near impossibility. Yet we have built colossal detectors, vast underground cathedrals filled with thousands of tons of purified water or liquid argon buried deep beneath mountains to shield them from all other forms of radiation, all in the hope of catching a rare fleeting glimpse of a single neutrino interaction. We have succeeded, and in doing so, we have opened a new window onto the universe. We use neutrinos to study the hidden heart of our own sun, to watch stars explode from the inside out light years away. But these incredible feats are just the beginning, because the true promise of the neutrino lies not in studying the universe as it is today, but in its potential to reveal the universe as it was in its most secret and formative youth. Let us journey back once more, back through the eons, past the age of galaxies and stars, back even before that wall of light at 380,000 years. Let us plunge deep into the primordial furnace to a time when the universe was not years, but just 1 second old. The temperature was not thousands of degrees, but a staggering 10 billion degrees. The cosmos was a crushingly dense soup of particles 1 billion times denser than water. In this extreme environment, even the reclusive neutrino could not travel freely. The universe was so tightly packed that neutrinos, for the one and only time in cosmic history, were held in thermal equilibrium with the rest of creation. They bounced off other particles exchanging energy, fully part of the cosmic scrum. The universe was opaque not only to photons but even to its ghosts. But the expansion was relentless, and as that first second ticked over, the universe expanded and cooled just enough that the density dropped below the critical threshold for neutrinos. The frantic interactions became less frequent. The space between particles grew. And just as light would do 380,000 years later, the neutrinos were set free. They decoupled from the rest of matter. They began to stream across the cosmos unimpeded, carrying with them a snapshot of the universe as it existed at the tender age of 1 second. This is a revelation of staggering importance. It means there is another cosmic background, an older, more fundamental echo of creation that has been travelling toward us for all of time. Not a background of light, but of ghosts, a cosmic neutrino background, the CNB. This is the ultimate fossil, a signal from an epoch 1/3 of a million years older than the CMB, an epoch that lies forever beyond the reach of light. These neutrinos were witnesses. They saw the universe before the first atoms existed. They felt the reverberations of cosmic inflation, the hypothesized moment of faster-than-light expansion that set the stage for the entire Big Bang. They were present for the great mysterious annihilation of antimatter, the event that left behind the tiny surplus of matter from which everything we know is made. The secrets to our deepest cosmic questions, questions we once thought unanswerable, are encoded in their energy and their distribution across the sky, in their very existence. If the cosmic microwave background is a baby picture, the cosmic neutrino background is a sonogram of the universe in the womb. It is the universe's oldest light, a light that isn't made of photons. For decades, this signal has been a pure prediction of our most trusted cosmological models. We are certain it is there, bathing the Earth, passing through us at this very moment. A relic sea of primordial neutrinos now cooled by cosmic expansion to a temperature of just 1.9 degrees above absolute zero, even colder and fainter than the CMB. But its existence poses a monumental challenge. How do you photograph a ghost? How do you capture a particle whose defining characteristic is its refusal to be captured? How do you build a telescope for the most elusive messenger in the cosmos? This is the new frontier, the grand quest for the next generation of cosmology. To finally detect this phantom signal, to open our eyes to this new kind of light, would be to push past the wall of fire that has defined the edge of our knowledge for a century. It would be to finally see older than light and to read the first page in the story of our universe. What if the most profound story in existence, the true origin story of everything you see, has been screaming at us since the dawn of time and we have been utterly deaf to it? What if the brightest light in the cosmos, the very echo of creation we have long celebrated as our oldest window to the past, is in fact a veil, a beautiful, brilliant but ultimately blinding curtain that conceals an even older, more fundamental truth? To see beyond it, we cannot look for light. We must instead learn to perceive the universe's most perfect ghosts, to hunt for the faintest whispers of a time before light could even travel freely. We must search for a phantom that has been passing through your body, through this very planet, every single second of your life. Billions of them, a silent, invisible torrent flowing from the heart of the Big Bang, journeying across 13.8 billion years of expanding space-time, and they do not stop. They do not slow. They do not collide. They are the universe's most reclusive and enigmatic messengers, and their story is our own. They are the neutrinos. To understand their cosmic significance, to grasp why they hold the key to the universe's first second, you first have to appreciate just how bizarrely, frustratingly insubstantial they are. A neutrino can travel through a light year of solid lead without ever disturbing a single atom. It is a particle so divorced from the world of matter that it borders on being a mathematical abstraction, a ghost in the grand machinery of physics. For decades, that's precisely what it was. Its story begins not with a discovery in a telescope, but with a crisis in a laboratory and a moment of scientific desperation. In the early 1930s, physics was grappling with a terrifying anomaly. In certain radioactive decays, a process known as beta decay, the fundamental laws of the universe appeared to break down. Energy, that most sacred and conserved quantity in all of science, was inexplicably vanishing. It was as if you dropped a glass and instead of shattering with a predictable release of sound and kinetic force, it simply stopped halfway to the floor, its potential energy absorbed into nothingness. For physicists, this was an existential threat. The conservation of energy was not just a rule, it was the bedrock upon which all of modern physics was built. Into this crisis stepped the brilliant but famously critical Austrian physicist Wolfgang Pauli. He was a man known for his brutal intellectual honesty, once remarking of a colleague's paper, "It is not even wrong." Faced with the apparent collapse of a foundational law, Pauli saw only two possibilities. Either physics was fundamentally broken, or something was escaping the scene of the crime, something invisible, undetectable, and carrying away the missing energy. In a famous 1930 letter to his colleagues, which he began with the address, "Dear radioactive ladies and gentlemen," Pauli proposed a radical, almost heretical idea. He suggested the existence of a new particle, a neutral, incredibly light and fantastically elusive entity that would balance the energetic books. He was so hesitant about postulating a particle that could not be seen a fix that seemed almost too convenient that he famously confessed, "I have done a terrible thing. I have postulated a particle that cannot be detected." He called his invention a neutron, a name later taken by a much heavier particle, but the concept was born. It was a ghost conjured out of pure theoretical necessity, a phantom designed to save the soul of physics. For more than 2 decades, that is all the neutrino remained an elegant solution, a clever hypothesis, a ghost in the equations. Catching such a ghost seemed impossible. How do you build a net for something that feels nothing for a particle that views solid matter as empty space? The challenge was monumental, requiring not just ingenuity but brute force. It would take 2 brilliant American physicists, Frederick Reines and Clyde Cowan, and the most powerful source of particles on Earth. In the mid-1950s, they devised a daring experiment they codenamed Project Poltergeist. They needed a source that would produce an unimaginably dense flood of neutrinos, a torrent so thick that by sheer statistical probability, 1 or 2 might finally interact. They found their source in the churning heart of a nuclear fission reactor at the Savannah River plant in South Carolina. A nuclear reactor is in essence a man-made star, a controlled inferno of beta decay, unleashing a staggering 100 trillion neutrinos per square centimetre every single second. This was their celestial blowtorch aimed at a sophisticated trap. Their detector consisted of massive tanks filled with over 200 litres of water laced with cadmium chloride. The theory was as elegant as it was audacious. If a neutrino, specifically an antineutrino from the reactor, struck a proton in a water molecule, it would create a positron and a neutron. The positron would instantly find an electron and annihilate in a telltale flash of gamma rays. The neutron, meanwhile, would wander for a few microseconds before being captured by a cadmium nucleus, an event that would produce a second distinct flash of gamma rays. The signature they were hunting for was this specific 2-step burst of light, a double tap separated by a few millionths of a second. It was the faintest of signals buried in a cacophony of background radiation from cosmic rays and the reactor itself. Reines and Cowan and their teams sat for months shielding their detectors, refining their electronics and watching. They were listening for the whisper of a ghost amidst a nuclear hurricane, and then in 1956 they found it. The double flashes appeared precisely as predicted at a rate that perfectly matched the reactor's operation. They sent a telegram to Wolfgang Pauli 26 years after his terrible suggestion. The message was simple, a testament to the profound journey from desperate hypothesis to physical reality. It read, "We are happy to inform you that we have definitely detected neutrinos. The ghost was real. This monumental discovery did more than just confirm a particle's existence. It solidified our understanding of the subatomic world and armed us with the knowledge that the universe was populated by these ethereal messengers. But no one, not even Reines and Cowan, could have imagined that this same ghostly particle held the secret to looking back to the very first second of time itself. To understand that secret, we must take a step back and look at the grand narrative of our cosmos, the Big Bang Theory. It is the triumphant story of modern cosmology, a model that describes a universe born from an infinitesimally small, unimaginably hot and dense state. From this primordial furnace, space itself began to expand, carrying energy and matter. with it cooling and thinning as it grew. Over billions of years, this expansion would lead to the formation of galaxies, stars, planets, and eventually us. But the Big Bang was more than just a compelling idea. It was a scientific theory, and that meant it made testable predictions. The most significant of these predictions was that the searing, brilliant energy of the initial creation should not have simply vanished. As the universe expanded, the wavelength of that primordial light would have been stretched, its energy diluted, cooled over the eons to a faint cold glow that should permeate all of space, a residual heat from the forge of creation. For decades, this prediction remained purely theoretical. Then, in 1964, came one of the most important discoveries in the history of science, and it arrived not with a bang, but with a hiss. At Bell Labs in New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were using a large horn-shaped antenna to study faint radio signals from the Milky Way. But they were plagued by a persistent low-level background noise. It was a faint microwave hum coming from every direction in the sky, day and night, season after season. It was uniform, constant, and utterly inexplicable. They checked their equipment, rewired their systems, and even famously removed a pair of pigeons that had been nesting in the antenna, cleaning out what they delicately referred to as white dielectric material. Yet the hiss remained. It wasn't an equipment malfunction, nor was it an earthly signal. It was cosmic. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists led by Robert Dicke was actively building an experiment to search for the very same thing. When the two groups finally connected, the truth became electrifyingly clear. Penzias and Wilson had accidentally stumbled upon the afterglow of the Big Bang. This cosmic microwave background, the CMB, was the echo of creation. The discovery of the CMB was a watershed moment transforming cosmology from a field of speculative theory into a precision science. It was the universe's baby picture, a snapshot of what the cosmos looked like when it was just 380,000 years old. Before this time, the universe was a blazing opaque fog. It was so hot and dense that atoms could not form. Instead, a plasma of free-roaming electrons and atomic nuclei filled all of space. Photons, the particles of light, were trapped in this cosmic soup, unable to travel more than a few feet without being scattered by an electron like light in a dense fog. The universe was hot, but it was dark. But as space expanded, it cooled. When the temperature dropped to about 3,000 degrees Kelvin, a critical threshold was crossed. Electrons and nuclei could finally combine to form the first stable atoms, mostly hydrogen and helium. Suddenly, with the electrons locked away inside atoms, the fog lifted. The universe became transparent. The photons that were present at that exact moment were set free, released to travel across the cosmos unimpeded. The light we detect today as the cosmic microwave background is that very light, its journey finally ending in our telescopes 13.8 billion years later. It is a stunning triumph of scientific prediction, a pillar of our modern understanding and our oldest direct image of the cosmos. But here is where the story takes its most tantalizing turn. The same Big Bang model that so perfectly predicted the CMB, this light from a 300,000-year-old universe, actually predicts that there should be two relic backgrounds from the early universe, not one. The CMB is the second echo, the younger of the two. There should be another far older message, a backdrop of particles released not when the universe was a sprawling toddler of 380,000 years, but when it was a mere infant just 1 second old. This older message is not carried by photons, but by the universe's ghosts, the neutrinos. To see why we must wind the cosmic clock back further past the era of the first atoms, past the lifting of the cosmic fog, all the way back to the first second of existence. In that maelstrom, the universe was an almost unimaginable furnace, billions of times hotter than the core of our sun. It was a seething soup of fundamental particles, quarks, electrons, positrons, photons, and crucially neutrinos. At this stage, the universe was so dense that even the ghostly neutrinos which can pass through LEAD today could not travel freely. They were constantly interacting with other particles through the weak nuclear force trapped in the primordial plasma, just as light would be for hundreds of thousands of years to come. But the universe was expanding and cooling at a ferocious rate. and as the temperature and density dropped, a moment of profound transformation occurred. When the cosmos was about 1 second old, the density of the particle soup fell below a critical threshold. The weak nuclear force which governs neutrino interactions became too feeble to keep them contained. The universe simply became too big and too empty for the neutrinos to find anything to interact with. In an event known as neutrino decoupling, the entire population of primordial neutrinos was set free from the cosmic scrum. They began to stream across the universe unimpeded, carrying with them a perfect snapshot of the cosmos at the age of 1 second. While light remained trapped in the fog for another 380,000 years, bouncing from particle to particle, its memory of the initial conditions becoming blurred, the neutrinos were released pristine and untouched. They are the true first messengers. The background of these ancient particles, the cosmic neutrino background or CNB, is the real ultimate prize. The CMB tells us the story of the universe's transition from an opaque plasma to a transparent gas of atoms. It is a story of chemistry and physics. But the CNB, born from that first second, would tell us a story of pure fundamental particle physics at energies we can never hope to replicate on Earth. It holds the secrets of the initial balance of matter and antimatter, the properties of the weak force in extreme conditions, and perhaps even clues to the nature of dark matter. It is a direct window into the physics that governed the birth of reality itself, and yet we have never seen it. Its existence is a firm, non-negotiable prediction of our most successful cosmological theory, its presence demanded by the same logic that gave us the CMB. So, where is it? The answer lies in the very nature of the ghost particle itself, and in the 13.8 billion years of cosmic history that separates us from its creation. Just as the CMB light was stretched and cooled by cosmic expansion, so too were the neutrinos of the CNB. But because they were released so much earlier when the universe was so much hotter, they have been stretched and cooled far, far more. Today these ancient neutrinos are staggeringly faint. Their energy has been diluted to almost nothing. While the CMB photons have a characteristic temperature of 2.7 Kelvin, just a few degrees above absolute zero, the CMB neutrinos are predicted to be even colder at a mere 1.9 Kelvin. More importantly, their kinetic energy is minuscule, thousands of times less than the neutrinos produced by the sun or nuclear reactors. They are the slowest, coldest, most lethargic particles imaginable. They are still flowing through us, billions of them every second, but they are cosmic spectres moving with so little energy that they have become almost impossible to distinguish from nothing at all. Detecting one is not like catching the ghost from Project Poltergeist, which was energized by a nuclear furnace. It is like trying to feel the impact of a single falling feather in the middle of a Category 5 hurricane. It is trying to find a message written in an ink that has faded to complete transparency. The triumph of the CMB discovery has for half a century cast a long shadow obscuring this deeper, more fundamental challenge. We have found the echo of creation, but we remain deaf to its first primordial scream. The Big Bang theory stands on the pillar of the CMB, but it rests on the ghost of the CNB. If it's there, our understanding of the first second is vindicated. If it is not, then our entire cosmic story may need to be rewritten. We stand at the edge of a new cosmological frontier, armed with the knowledge of what must be there, but haunted by the immense difficulty of seeing it. The script of the first second has been written. The challenge now is to find a way to read it. And so, if this primeval sea of neutrinos truly exists, what should it look like? What signature should we be searching for? Our theories of cosmology are not mere speculation. They are predictive machines capable of winding the clock back to the universe's first fractions of a second and telling us with stunning precision what we ought to find. They provide a detailed blueprint for a ghost, a forensic profile of a particle that has been hiding in plain sight for 13.8 billion years. The first most fundamental prediction is its temperature. When the cosmic microwave background was released, the universe had a blistering temperature of around 3000 Kelvin. Today, stretched by cosmic expansion, those photons have cooled to a mere 2.725 Kelvin, just a whisper above absolute zero. You might expect the relic neutrinos to be at this same temperature, having marinated in the same expanding cosmos for the same duration. But here the story takes a subtle and beautiful turn. The neutrinos, as we saw, decoupled earlier than the photons. After they began their lonely journey but before the photons were set free, a momentous event occurred in the cooling universe. The temperature dropped low enough that electrons and their antimatter counterparts positrons could no longer be spontaneously created from pure energy. With their creation engine shut off, the existing pairs began to find each other in a final frantic dance of annihilation. For a time, the cosmos was lit by a continuous blaze as matter and antimatter vanished into pure light. This massive injection of energy didn't affect the already departed neutrinos. They were oblivious, streaming freely through the chaos, but it poured directly into the photon baryon fluid like stoking a dying fire. It gave the photons a significant thermal boost, reheating them relative to the neutrinos. Our calculations anchored in the immutable laws of thermodynamics predict this reheating effect with exquisite accuracy. The result is a concrete testable difference. The cosmic neutrino background today should be colder than the cosmic microwave background. Its predicted temperature is not 2.7 Kelvin, but a frigid 1.95 Kelvin. A tiny difference, yet one that carries the echo of the universe's first great annihilation event. From temperature we can derive density. The prediction is as staggering as it is precise. Flowing through every single cubic centimetre of the universe right now, there should be an average of 336 of these ancient neutrinos. Think about that. In the small volume of air cupped in your hands, more than 1,000 particles born in the first second of time are silently passing through. They stream through your body, through the bedrock of the continents, through the dense iron heart of the planet itself, as if it were all empty space. They are the most numerous particles in the universe after photons of light, a constant invisible rain falling through everything everywhere for all time. Their sheer number is almost beyond comprehension, an omnipresent ocean of relics from a time before atoms. And just as with the CMB, our models predict their energy distribution. They should follow a perfect thermal spectrum, a bell curve dictated by their 1.95 Kelvin temperature. However, unlike the CMB photons, which all travel at the speed of light, these neutrinos now move much more slowly. Expansion has robbed them of their primordial momentum, leaving them as a cold, lethargic gas. Their kinetic energy is minuscule, thousands of times lower than any neutrino ever detected by our instruments on Earth. This then is the profile of our quarry. A sea of particles colder than the background light with a specific density and an impossibly low energy. With such a clear set of predictions, the task seems straightforward. Build a detector pointed at the sky and confirm their existence. Here, however, we collide with one of the most profound experimental challenges in the history of science. To understand the difficulty, you must first appreciate the relative ease of seeing the cosmic microwave background. A photon, the particle of light, is an electromagnetic creature. It interacts readily. When a CMB photon strikes the antenna of a radio telescope, it shakes the electrons within the metal, inducing a tiny electrical current. The interaction is robust, reliable. We can build vast sensitive dishes that act like cosmic fishing nets, catching these ancient photons by the billions, allowing us to map their glow with breathtaking precision. The CMB is not a whisper. It is a persistent, luminous hum that fills the entire sky, accessible to anyone with the right kind of radio. We haven't just seen it. We have photographed it in high definition. Detecting a relic neutrino is an entirely different kind of problem. It is like trying to catch a phantom with a net made of fog. Neutrinos do not feel the electromagnetic force. They are immune to the siren call of positive and negative charge that governs nearly all of our everyday world. They are ghosts in the machine. Their only way of speaking to the universe of normal matter is through the weak nuclear force, a fundamental interaction so feeble and so short-ranged that it is almost imperceptible. For a low-energy neutrino, the probability of interacting with a single atom is so infinitesimally small that it beggars belief. You could build a shield of lead 1 light-year thick, stretching from here to the nearest star. And most of these relic neutrinos would pass straight through it without leaving a single trace. They mock our most substantial barriers. This is why they are able to stream unimpeded from the core of the Big Bang. But it is also why they are so maddeningly difficult to grasp. Our most sophisticated neutrino observatories, colossal instruments like Japan's Super Kamiokande or the ice cube array buried deep within the Antarctic ice sheet are marvels of engineering. They use thousands of tons of purified water or pristine ice lined with hypersensitive light detectors, waiting in absolute darkness. They are designed to catch the flash of light produced when a rare, high-energy neutrino, perhaps from the Sun, or a distant supernova finally smashes into an atomic nucleus. These detectors are humanity's ghost traps, yet even they are completely blind to the cosmic neutrino background. The problem is one of energy. A high-energy neutrino strikes a nucleus with the force of a subatomic bullet shattering it and creating a shower of detectable secondary particles. But a relic neutrino with its tiny kinetic energy is not a bullet. It is a piece of cosmic dust. It drifts up to a nucleus and simply bounces off. The interaction known as coherent elastic scattering imparts a recoil so gentle, so indescribably small, that the targeted nucleus barely moves. The energy it deposits is far, far below the threshold of what any existing detector can sense. It's like trying to measure the impact of a single falling feather on a battleship. The effect is there in theory, but it is lost in the noise of a vibrating world. We are surrounded by a literal ocean of these particles, yet we lack the technology to feel the water. Direct detection of the CNB remains a holy grail for experimental physics, a dream for a future generation of technology that does not yet exist. It seems then that we are at an impasse. The universe's oldest message is constantly washing over us, but we cannot read it. Its most profound secret is being whispered in our ears, but we are deaf to its frequency. But this is not where the story ends, for even if we cannot catch the ghost itself, we can search for its shadow. We can become cosmic detectives looking not for the particle, but for the subtle influence it has on everything around it. While the neutrinos may not interact with matter directly, they do possess energy and a tiny amount of mass. And where there is mass and energy, there is gravity. Gravity is the one force the neutrino cannot ignore. It is the universe's great communicator, a force that reaches across the void felt by everything. By searching for the faint gravitational accent of 336 neutrinos in every cubic centimetre of space, we have found a way to prove their existence indirectly, but irrefutably. Our investigation begins in the crucible of the early universe during the period known as Big Bang nucleosynthesis. In the first 3 minutes of time, the entire cosmos was a single sprawling nuclear reactor. It was so hot and so dense that protons and neutrons were fusing together, forging the first atomic nuclei. The universe was manufacturing its own building blocks, hydrogen, helium, and trace amounts of lithium. The outcome of this cosmic alchemy was extraordinarily sensitive to one critical factor, the expansion rate of the universe. The faster the universe expanded, the more quickly it cooled. A faster expansion meant less time for neutrons and protons to find each other and fuse. It would leave behind more unburnt hydrogen and produce less helium. A slower expansion conversely would allow for more thorough nuclear reactions, resulting in a higher abundance of helium. It's a beautifully simple cosmic clock. What then determined this expansion rate? The answer, according to Einstein's theory of general relativity, is the total energy density of the universe at that time. Everything that contained energy, photons, electrons, positrons, baryons, and crucially neutrinos, contributed to a gravitational pressure that was driving space itself apart. When we run the equations of nucleosynthesis, we can precisely calculate what the primordial abundances of hydrogen and helium should be for a given expansion rate. We can then look out at the oldest, most pristine gas clouds in the distant cosmos places untouched by stellar evolution and measure their chemical composition. We can see what the universe actually made. The results are one of the great triumphs of modern cosmology. The measured abundances of helium-4, deuterium and helium-3 match the theoretical predictions with astonishing accuracy, but only if we include the energy density of a sea of weakly interacting particles. Specifically, the data tells us there must have been a contribution equivalent to 3 distinct species, or families, of light neutrinos. If there were only 2 families, the universe would have expanded too slowly, and we would see far more helium than we do. If there were 4, it would have expanded too quickly, and we'd see too little. The number is 3. The primordial elements forged in the fire of the first 3 minutes act as a standard candle for the energy density of the universe. Their measured abundances are a receipt from the cosmos, a piece of hard evidence that testifies to the existence of a vast population of neutrinos, acting as a form of invisible radiation, shaping the expansion and the very composition of the nascent universe. This was the first hint, the first piece of circumstantial evidence that the CNB was not just a theoretical fantasy. The first atomic nuclei are its witnesses. Our second line of evidence comes from an even older light, the cosmic microwave background itself. When we look at the map of the CMB, we see that it is not perfectly uniform. It is mottled with tiny variations in temperature hot and cold spots that vary by only 1 part in 100,000. These minuscule fluctuations are of monumental importance. They are the seeds of all cosmic structure, the primordial lumps and voids from which every galaxy and every galaxy cluster would eventually grow. Before they were released as the CMB we see today, the photons were trapped in a dense opaque plasma with protons and electrons. This plasma was not static. It was ringing like a colossal bell. Gravity would pull matter into the denser regions, compressing and heating the plasma. But the intense pressure from the trapped photons would push back, causing the plasma to expand and cool. This cosmic tug-of-war between gravity pulling in and radiation pressure pushing out created vast sound waves, acoustic oscillations that sloshed back and forth through the primordial fluid. The hot and cold spots in the CMB are a direct snapshot of these sound waves frozen in time at the moment the universe became transparent. Now, where do the neutrinos fit into this picture? Remember, they had already decoupled. They were no longer part of the plasma. They were free-streaming ghosts passing through these dense, oscillating regions without interacting. They were not caught up in the sound waves, but they were still there and their gravity was still felt. Their immense numbers and collective energy density provided an additional gravitational pull on the plasma, subtly altering the dynamics of the sound waves. Imagine a pendulum swinging back and forth. This is like the plasma oscillating. Now imagine a gentle, persistent, invisible wind blowing on that pendulum. It won't stop the swinging, but it will slightly alter its timing, its phase, and the maximum height it reaches. The free-streaming neutrinos were that invisible gravitational wind. They created a subtle but predictable phase shift in the acoustic oscillations. They caused the compressions to be slightly deeper, and the rarefactions slightly shallower than they would have been otherwise. This specific signature is imprinted onto the statistical properties of the CMB map, particularly in the pattern of how the size of the hot and cold spots relates to their intensity. This pattern is captured in a graph called the CMB Angular Power Spectrum Cosmology's Rosetta Stone. When our space-based observatories from COBE to WMAP to the Planck satellite measured this power spectrum with ever-increasing fidelity, they found the neutrino's fingerprint waiting for them. The data points on the graph representing the real measured universe fall perfectly along a theoretical curve that assumes not only the existence of the cosmic neutrino background, but also its predicted temperature and density. The subtle gravitational drag of these relic particles acting on the plasma of the infant universe is etched into the patterns of the oldest light. The CMB is not just a baby picture of the cosmos, it is a crime scene, and the neutrinos left their gravitational DNA all over it. We cannot see them with our telescopes, but we can see the precise way they warped the fabric of space-time 380,000 years after the beginning. The final piece of the puzzle brings us forward in time from the infant cosmos to the grand, mature structures we see today. After the release of the CMB, those tiny density fluctuations began their slow, patient work. Over billions of years, gravity amplified them. Regions that were slightly denser than average pulled in more and more matter, collapsing to form the first stars' galaxies, and eventually the immense clusters of galaxies that define our cosmic neighbourhood. This process gave rise to the magnificent cosmic web, a vast interconnected filamentary structure of matter stretching across billions of light years. But the final shape and texture of this web depended critically on every ingredient in the cosmic recipe, including our elusive neutrinos. In the early stages of structure formation, the relic neutrinos were still moving at speeds very close to the speed of light. In cosmological terms, this makes them a form of hot, dark matter. Their high velocity gave them a tremendous amount of kinetic energy, which allowed them to resist the pull of gravity on smaller scales. Imagine trying to build a sandcastle with incredibly energetic, fast-moving sand. On large scales, you could still pile it into a large hill. But if you tried to sculpt a small delicate tower, the fast-moving grains would simply fly away, smoothing your structure out. The relic neutrinos did exactly this to the cosmic web. As they streamed across the cosmos, they tended to escape from smaller, lower-density gravitational wells, the places where small dwarf galaxies would have otherwise formed. This process, known as free-streaming suppression, effectively erased the smaller-scale structures smoothing out the cosmic web. A universe filled with these fast-moving neutrinos will therefore have fewer small galaxies and a slightly different statistical distribution of matter compared to a universe without them. This provides yet another powerful independent test. We can use vast astronomical surveys like the Sloan Digital Sky Survey or the Dark Energy Survey to create immense three-dimensional maps of the distribution of millions of galaxies. We can meticulously measure how galaxies cluster on different scales. We can count the number of galaxy clusters of a certain mass. When we compare these detailed observations of the modern universe to our computer simulations, the results are once again unambiguous. The observed structure of the cosmic web, the way galaxies are scattered across the heavens, is only consistent with a universe that contains a background of relic neutrinos, possessing the properties predicted by our standard cosmological model. The very architecture of the cosmos, the placement of galaxies on their gossamer threads, is shaped by the gravitational influence of this invisible population. They are the unseen sculptors of the cosmic web. Big Bang nucleosynthesis, the anisotropies of the cosmic microwave background, the large-scale structure of the universe, three completely different epochs in cosmic history, three completely different sets of physical phenomena, and three completely different types of astronomical observation. From the forging of the first nuclei in the first minutes to the ringing of the primordial plasma for millennia to the patient construction of galaxies over billions of years, each one, when interrogated, tells the exact same story. They all bear the unmistakable imprint of a cold, vast and ancient sea of neutrinos. We have not yet managed to capture one of these particles in a laboratory. We have not directly felt its whisper against our detectors, but we have seen its shadow cast across the entire history of the cosmos. We have weighed its gravitational influence. We have proven beyond any reasonable doubt that it is real. The ghost is not a fantasy. It is a pervasive fundamental component of our reality. The question is no longer if the cosmic neutrino background exists. The question, now the driving obsession for a new generation of scientists, is how do we finally build a machine sensitive enough to reach out and touch the ghost? And so we found ourselves in a cosmic paradox. We had seen the shadow of these primordial messengers, their faint gravitational fingerprint pressed into the afterglow of creation, their influence subtly steering the alchemy of the first 3 minutes. We knew with a certainty forged in the mathematics of the cosmos that we are swimming right now in an ocean of these relic neutrinos, 10 trillion of them flooding through your body every second. They are the oldest story in the universe, a message in a bottle, thrown from the shore of the Big Bang itself. And yet the bottle was invisible, its message written in an ink so faint it seemed destined to remain unread forever. The indirect evidence was a tantalizing whisper from behind a locked door, confirming someone was there but offering no way to see their face. For decades, the challenge of direct detection felt less like a scientific problem and more like a philosophical barrier, a fundamental limit on what we could ever hope to know. How do you catch a ghost? Especially a ghost that has been travelling for 13.8 billion years, a journey that has stretched its wavelength and bled away almost all its kinetic energy, leaving it cosmically cold, barely interacting with anything at all. The energy of a solar neutrino itself, famously elusive, is a roaring bonfire compared to the dying ember of a relic neutrino. They simply don't have the punch to trigger our conventional detectors, those vast cathedrals of water or liquid scintillator waiting for a telltale flash of light. A relic neutrino would drift through them all without a sound, a silent testament to a universe we could model but never touch. The problem was twofold, and each facet was a monster of cosmic proportions. First, this profound energy deficit. The particles were real, but they were impotent, lacking the momentum to knock an electron from its orbit or shatter an atomic nucleus. They carried the information, but they refused to speak. The second, and perhaps even more daunting, was the noise. Our planet is a cacophony of particle interactions. The sun bombards us with trillions of higher energy neutrinos. Nuclear reactors hum with their own artificial neutrino flux. Cosmic rays shatter atoms in the upper atmosphere, creating showers of secondary particles. Even the natural radioactivity in the rock beneath our feet contributes to the din. Trying to find the signal of a single relic neutrino in this storm was like trying to hear a single grain of sand fall in the midst of a volcanic eruption. It seemed not just difficult, but a sheer absurdity. This is where the story of science so often turns. When brute force fails, when building a bigger net or a more sensitive microphone is no longer enough, a new kind of thinking is required, a leap of imagination. The quest for the cosmic neutrino background had to move from the realm of bigger engineering to deeper, more elegant physics. We had to stop trying to listen for a shout and instead learn to detect the absolute quietest of whispers. The breakthrough would not come from a bigger bucket, but from a more clever key designed for a lock nobody had ever thought to look for. The revolution began with a question that reframed the entire problem. What if we stopped trying to catch a neutrino by what it does to a target, the energy it deposits, the flash of light it creates? What if instead we could detect its mere presence? What if we could find a process in nature so exquisitely sensitive, so perfectly balanced on a knife's edge that the gentle nudge of a relic neutrino's existence could tip the scales? This was the dawn of a new strategy, not to look for a collision, but to look for a catalyzed transformation. An event that could only happen if one of these cosmic ghosts was present to officiate. Physicists turned their gaze away from brute force interactions and toward the subtle quantum dance of radioactive decay. Specifically, they looked at the most common form of decay-beta decay. It's a foundational process of our universe. Inside an unstable atomic nucleus, a neutron, a neutral particle, transforms itself. It becomes a positively charged proton, and in the process it spits out a negatively charged electron and a tiny ghostly antineutrino. This process has been studied for a century. It is the reason certain elements are radioactive. But within this familiar decay lay the seed of a truly radical idea. Physics loves symmetry. If a process can run one way, it can often be forced to run in reverse. If a neutron can decay into a proton, an electron, and an antineutrino, could a proton with some encouragement do the opposite? Yes! It's a process called electron capture, where a proton inside a nucleus grabs one of its own orbiting electrons, and the two merge, transforming the proton into a neutron and emitting a neutrino. It happens. But the truly beautiful idea came from taking this one step further. What if instead of capturing an orbiting electron, a neutron could be created by having a proton capture a free-flying neutrino? This was the conceptual key. The process known as inverse beta decay was theoretically sound. A neutrino strikes a neutron, and the neutron transforms into a proton while emitting an electron. Or in a slightly different flavour of the same reaction, a neutrino can be captured by a nucleus changing its identity. This was no longer about a billiard ball collision. This was a quantum transaction. The neutrino wouldn't just be a projectile, it would be a reactant, a fundamental ingredient in a nuclear recipe. The challenge then was to find the perfect nucleus to serve as the target an atom whose internal structure was uniquely receptive to being transformed by the whisper of a relic neutrino. The search led scientists to an isotope of hydrogen, the simplest element in the universe. Not ordinary hydrogen with its single proton, nor deuterium with a proton and a neutron. It led them to tritium, an exotic radioactive form of hydrogen with one proton and two neutrons in its nucleus. Tritium was, for a confluence of reasons, the miracle candidate. It was the dream detector in a single atom, and the reason for its perfection lies in its own instability. You see, tritium is naturally radioactive. Left on its own, one of its neutrons will undergo beta decay, turning into a proton. The tritium atom, with its one proton and two neutrons, transforms into a stable helium-3 atom, which has two protons and one neutron. In the process, it releases an electron and an antineutrino. This natural decay was both the greatest challenge and the greatest opportunity. The challenge was obvious. A sample of tritium is constantly emitting electrons on its own. This creates a massive background signal, a roar of noise that could easily drown out the faint signal we're looking for. But the opportunity was pure genius. It arose from a deep understanding of the energies involved. When a tritium nucleus decays, the energy released is shared between the outgoing electron and antineutrino. This means the electrons come out with a whole spectrum of different energies, a continuous smear from near zero up to a very specific maximum value. This maximum, known as the Q value or the endpoint energy, is the absolute speed limit for an electron from this decay. It occurs in the rare case where the antineutrino is born with virtually zero energy, allowing the electron to fly away with all the available kinetic energy from the reaction. This endpoint is the key to everything. It is a hard wall. No electron from the natural spontaneous decay of tritium can ever have more energy than this specific value, about 18.6 kilo-electron volts. Now consider what happens if a cosmic relic neutrino comes along. It has very little kinetic energy from its long journey, but it still possesses its own intrinsic mass, a tiny bit of energy, locked away by Einstein's E-f-sistu. If this relic neutrino is captured by a tritium nucleus, it triggers an inverse beta decay reaction. A neutrino plus tritium yields helium-3 plus an electron. The electron that flies out of this reaction is special. It carries all the energy from the nuclear transformation I+, the tiny extra bit of rest mass energy donated by the captured neutrino. And that is the signature. The unmistakable smoking gun. The electron created by relic neutrino capture will have an energy that is slightly higher than the maximum possible energy from normal beta decay. It would appear as a tiny sharp spike in the energy graph sitting just beyond the endpoint where no signal should exist. It would be a signal emerging from absolute silence, a single voice singing a note just above the range of the entire orchestra. It wouldn't just be evidence, it would be a measurement. The exact position of that spike would tell us the mass of the neutrino, one of the most sought-after unknown values in all of physics. The sheer elegance of this idea is breathtaking. It solves both of the monumental problems at once. You're no longer looking for a powerful collision. You're looking for a quantum mechanical cheat, a particle that appears with a forbidden amount of energy thanks to the neutrino's contribution. And you're no longer trying to hear a whisper in a hurricane. You've found a frequency that the hurricane cannot produce. The natural decay of tritium creates the background noise, but it also creates a perfect silent window just beyond its own limit, a pristine patch of reality where only the signal from the Big Bang can appear. This was the conceptual leap that moved the detection of the cosmic neutrino background from the realm of impossibility into the realm of the merely heroically difficult. But the word difficult barely begins to capture the scale of the undertaking. The theoretical framework was a masterpiece of ingenuity, but translating it into a physical experiment would require pushing technology to its absolute breaking point and perhaps beyond. It would demand the construction of some of the most ambitious, sensitive and complex scientific instruments ever conceived. First, you need your target. The probability of any single tritium atom capturing a relic neutrino in a given year is infinitesimally small. To get even a handful of these events, perhaps just a few per year, you don't need a small vial of tritium. You need a colossal amount. The dream experiments call for on the order of 100 grams of pure tritium gas. This by itself is a staggering challenge. Tritium is rare radioactive with a half-life of only 12 years and incredibly difficult to handle. 100 grams of tritium represents more than 1 million curies of radioactivity. It is a substance primarily associated with the thermonuclear cores of hydrogen bombs. Containing it safely at cryogenic temperatures while allowing it to be observed by a detector is an engineering problem of the highest order. You need a vast complex circulatory system of pumps and purifiers, all operating with a level of integrity that allows for no leaks ever. The source itself, the heart of the experiment, would be a technological marvel. Then you need to be able to precisely measure the energy of every single electron that emerges from that gas. You need an electron spectrometer, but not just any spectrometer. It needs a resolution so fine and accuracy so perfect that it can distinguish an electron with an energy of 18,600 kilo-electron volts from one with an energy of 18,601 kilo-electron volts. This requires a machine of gargantuan scale. The leading design for such a device is a magnetic colossus, a vast chamber tens of meters long, wider than a house, inside of which a precisely controlled magnetic field acts like a gigantic lens. This magnetic river guides the electrons from the tritium source on a long looping journey. Faster electrons, those with more energy, will trace a wider arc than slower ones. By tuning the magnetic field with incredible precision, you can create an energy filter, allowing only those electrons in a very narrow energy window to reach the detector at the far end. Imagine a machine the size of a small building built with the precision of a Swiss watch, held at a near-perfect vacuum and permeated by magnetic fields controlled to a few parts per million. This isn't just a detector. It's an atomic-scale sorting facility designed to sift through trillions upon trillions of electrons from normal decay to find the 1 or 2 golden electrons per year that carry the secret of the Big Bang. The sheer scale is born of necessity. To get the required energy resolution, the electrons need a long flight path to allow their trajectories to separate. It is a brute force approach to achieving an almost supernatural level of finesse. And finally, you must build this entire delicate apparatus in the quietest place on Earth. You must silence the cosmic noise. This means going deep underground beneath hundreds of meters of solid rock to shield the experiment from the constant rain of cosmic rays. It means constructing the detector from materials that have been meticulously selected for their ultra-low intrinsic radioactivity materials that have been stored underground for years, shielded from cosmic ray activation. It means surrounding the entire setup with layers of active and passive shielding, tons of lead-copper, polyethylene, and water, an elaborate cocoon designed to stop any stray particle from the outside world from getting in and faking the signal you so desperately seek. You're trying to create a small pocket of the universe that is more silent, more pristine than interplanetary space itself. This is the anatomy of a dream, an audacious vision for a machine that could finally see the universe as it was in its very first second. Experiments with names like Ptolemy are now on the drawing board, the blueprints for this incredible quest. They build on the legacy of their predecessors, like the Katrin experiment in Germany, which, while designed to measure the neutrino mass using the same tritium endpoint, has simultaneously perfected the very technologies needed to hunt for the CNB. Katrin is the monumental proving ground, a 70-metre-long behemoth that has shown us that building spectrometers of this scale and precision is possible. It has paved the way, demonstrating the feasibility of the tools we now hope to turn toward an even more profound cosmic question. For the first time since the dawn of cosmology, a plausible, albeit profoundly difficult path to directly detecting the cosmic neutrino background now lies before us. The theoretical elegance of using neutrino capture on tritium has given us a target and a signature. Decades of technological progress have given us the tools to build the immense, ultra-precise machines required. The wall of impossibility has not vanished, but it has begun to crack. We can now see through the fissures, and what we see on the other side is a glimpse of the universe's infancy, a message that has been waiting patiently for us to build a machine clever enough and quiet enough to finally receive it. The dream now has a blueprint. The quest for the oldest story ever told has truly begun. We have chased this cosmic ghost through the echoes of space-time. We have followed its trail back to the very first second of existence, a time before the first star, before the first galaxy, to a universe so dense it was a single searing point of incandescent plasma. We know our target now. Not a flash of light, but an impossibly faint cold whisper. A whisper that has been travelling unimpeded for 13.8 billion years. To hear it to finally capture one of these primordial messengers, the upward gaze of cosmology is not enough. Our journey must now turn inward and downward. It must leave the realm of elegant theory and descend step by painstaking step into the brutal, demanding world of physical reality. Because to find the quietest, oldest signal in the universe, you must first build the quietest place on Earth. This is not a task of astronomy. It is a Herculean feat of engineering, a crusade against the fundamental noise of our own world. The problem is immense, almost philosophical in its scale. You're trying to detect a particle carrying a whisper of energy less than a millionth of the energy of the electron orbiting a hydrogen atom. This ephemeral touch is the prize. But our planet, our galaxy, our very bodies are screaming with energy. We are bathed in a constant roaring hurricane of radiation, a symphony of interference that would utterly drown out the delicate signal we seek. The first movement in this symphony is the roar from above. Cosmic rays. These are not gentle waves of light. They are atomic nuclei protons and heavier elements forged in the hearts of exploding stars and flung across interstellar space by the unimaginable forces of supernova and the swirling magnetic fields of active galactic nuclei. They are celestial shrapnel travelling at nearly the speed of light. Every second, hundreds of these particles are tearing through your body, striking the atmosphere above us and creating a shower of secondary particles, muons, pions, a cascade of energetic debris that rains down upon the surface, a constant high-energy static. To our neutrino detector, each one of these cosmic ray impacts would be a blinding flash, a thunderclap that would make the whisper of the Big Bang impossible to discern. And this is only the noise from the heavens. The Earth itself, the very ground beneath our feet, is also a source of chaos. The rock, the soil, the air we breathe it, is all radioactive. This is not the result of some industrial contamination. It is the planet's own ancient primordial heartbeat. Since its formation, elements like uranium, thorium, and potassium have been trapped within its crust, and these atoms are unstable. Slowly, inexorably, over millions and billions of years, they decay. An atom of uranium does not simply sit still. It spontaneously shatters, releasing a burst of energy in the form of alpha particles, beta particles, and gamma rays. This is the planet-breathing radiation, a soft but persistent glow that emanates from the granite in our kitchen countertops, the concrete in our buildings, and the deep rock of the continental plates. For our detector, this gentle terrestrial hum is another form of overwhelming noise, a constant chatter of false signals originating from our own home. Every single gamma ray from a decaying potassium-40 atom in a nearby stone could perfectly mimic the signal we have spent decades searching for. The Earth, our cradle, becomes a cage of radioactive interference, so the challenge becomes one of isolation. How do you build a sanctuary, a chamber so perfectly shielded that the whispers of the early universe can finally be heard over the roar of the present? The solution is as profound as it is simple. You must use the Earth itself as a shield. You must go down. Deep, deep down. The journey into one of the world's deep underground laboratories is a descent into another reality. You step into an industrial cage, a mining elevator, and the steel doors close. The world above the sunlight, the wind, the noise of civilization vanishes. The elevator begins its plunge, 1 kilometre, then 2. You are falling through geological time past layers of rock laid down hundreds of millions of years ago, when life on the surface was just beginning to crawl from the oceans. The pressure in your ears changes. The air grows cool and still. The sheer weight of the planet is pressing in from all sides. And it is this immense burden of rock, this geological armour, that provides the first critical layer of protection. With every metre you descend, more of the cosmic ray shower is absorbed. The relentless hail of muons from the sky is stopped, filtered out by the stone. By the time you reach the laboratory level 2 kilometres beneath the surface, the cosmic ray flux has been reduced by a factor of more than 1 million. The roar from the heavens has been silenced to less than a whisper. The elevator doors open not onto a dusty mine shaft, but onto a scene of almost surreal cleanliness. You are in a vast excavated cavern, a cathedral of science carved from primordial gneiss or granite. Places like Snow Lab in Canada, buried in an active nickel mine, or the Gran Sasso National Laboratory in Italy, nestled in the heart of a mountain. These are not mere rooms. They are city blocks of scientific infrastructure hollowed out with immense effort, their walls sprayed with a special sealant to trap the radon gas seeping from the rock, another insidious source of radioactive noise. Here the silence is physical. It is a pressure, a palpable absence of the background chatter we live with every day. The journey downward is complete. The detector now sits behind a shield of stone more powerful than any man-made barrier could ever be. We have escaped the cosmic storm, but in doing so we have revealed a new, more intimate enemy, the noise from within. Having shielded your experiment from the universe and the planet, you now face the treacherous fact that the materials you use to build your detector are themselves radioactive. This is the great paradox of extreme precision measurement. Every component, every screw, every wire, every crystal is a potential traitor. The copper in the wiring, the steel in the support structure, the glass in the sensors, All of it contains trace amounts of the same uranium and thorium that we burrowed 2 kilometers underground to escape. These are not impurities in the industrial sense. They are contaminants on an atomic scale, a few rogue atoms in a billion. But in this game of ultimate sensitivity, a few atoms are more than enough to create a blinding fog of false signals. A single decaying nucleus inside the detector's core could be the event that sends a team on a months-long wild goose chase, celebrating a discovery that was never real. The quest for the cosmic neutrino background therefore becomes a crusade for purity, an obsessive, almost fanatical pursuit of materials so clean they barely seem to belong to our world. This pursuit drives scientists to the ends of the earth and back into history. Consider the problem of lead. Lead is an excellent shield against gamma rays, but freshly mined lead contains an isotope, lead-210, which is radioactive and creates a problematic background signal. The solution? You need old lead that has been sitting for centuries long enough for the lead-210 to have decayed away into stable silence. So teams have sourced their shielding from the most unlikely of places. They have reclaimed the ballast from ancient Roman cargo ships sunk in the Mediterranean. 2,000 years ago, their lead ingots resting on the seafloor, shielded by water from cosmic rays for millennia. This ancient quiet metal once used for plumbing and anchors in the Roman Empire is now melted down and reformed into pristine bricks that will protect some of the most advanced scientific instruments ever conceived. Every piece of material undergoes a similar rigorous journey. Copper is grown in special underground labs, electroformed in ultra-pure chemical baths, shielded from cosmic rays even as it's being created to ensure it is born clean. Welders are trained in special techniques to avoid introducing even microscopic specks of dust, and every single component before it is allowed anywhere near the experiment is placed in its own detector, a smaller, exquisitely sensitive device whose only job is to sit and listen sometimes for months to see if the material sings with the telltale tune of a radioactive decay. We are forced to build detectors to vet the materials to build our final detector. It is a dizzying recursive path toward absolute purity. Once the sanctum is built from these impossibly pure materials, the final challenge emerges: the enemy of heat. To us, a room at a comfortable temperature feels calm, but at the atomic level it is a scene of unimaginable violence. The atoms in the detector material are vibrating, jostling and crashing into each other billions of times per second. This thermal energy, this heat noise, creates a constant tremor in the detector's sensors. It is a jitter that would once again overwhelm the tiny delicate push from a relic neutrino. The signature we are looking for is so small that if the atoms of the detector itself are moving with any significant energy, the signal will be lost in the thermal chaos. We have shielded our experiment from the cosmos and from the Earth. We have purged it of its own atomic impurities. Now we must bring it to a state of near-perfect stillness. We must freeze it. The target temperature is not merely cold, it is a coldness that has no parallel in the natural universe save for the deepest voids of intergalactic space. We must cool the heart of the experiment to within a few thousandths of a degree of absolute zero. Absolute 00 Kelvin or minus 273. 15 degrees Celsius is the theoretical point at which all classical atomic motion ceases. It is the ultimate state of physical quiet. Achieving this is an engineering marvel. The core of the detector is placed within a cryostat, a high-tech thermos bottle of immense complexity. It is a series of nested concentric chambers like a Russian doll. Each layer is separated from the next by a vacuum preventing heat from conducting its way inward. The outer layers are cooled with liquid nitrogen, a relatively cheap and accessible coolant. This brings the temperature down to a brisk 77 Kelvin, but that is nowhere near cold enough. Inside this, a second layer is cooled with liquid helium, dropping the temperature to a mere 4 Kelvin. This alone is a monumental task requiring a closed-loop system of pipes and compressors to keep the precious boiling helium from escaping. And from this point, the final, most delicate descent begins. Sophisticated refrigeration techniques using the strange quantum properties of helium isotopes are employed to wick away the last vestiges of heat, pumping out energy phonon by phonon until the detector's core is suspended in a state of profound, unprecedented cold. At these temperatures, the frantic dance of atoms slows to a glacial crawl. The thermal jitter is silenced. The detector is finally calm enough, still enough to feel the gentle breeze from the dawn of time. This entire endeavour, this descent into the earth, this crusade for purity, this journey to the brink of absolute zero, is a testament to more than just technology. It is a testament to human patience and collaboration. No single person, or even a single nation, can build such a thing. Experiments like the proposed Ptolemy project are the work of a global village of scientists. Physicists who model the neutrino interactions, chemists who develop the purification techniques, engineers who design the cryogenic systems, geologists who certify the stability of the underground caverns, and computer scientists who write the algorithms to sift through the data. They come from dozens of institutions spanning continents united by a shared audacious goal. These projects are not completed in years but in decades. They are generational quests. A graduate student who helps design the shielding might be a tenured professor by the time the first data is collected. The scientist who first proposed the experiment might not live to see its final results. It requires a faith in the scientific process, a willingness to contribute one piece to a mosaic far larger than any single career. It is the slow, methodical, and often frustrating work of overcoming one seemingly insurmountable obstacle after another. It is the opposite of a sudden eureka-like breakthrough. It is a relentless grind toward perfection. And so, the stage is finally set. Deep beneath a mountain shielded from the cacophony of the cosmos, and the earth inside a fortress of the purest materials ever assembled by human hands and cooled to a stillness that borders on the absolute the instrument waits. We have created a pocket of profound silence and stability in a violent universe. We have built the most sensitive listening post in history. The downward path is complete, the fortress is sealed, the noise is gone. Now with the universe held at bay, we face the ultimate question. With our trap so exquisitely prepared, what precisely is the bait? How do we trick this ghost from the beginning of time into finally revealing itself? And so the trap is set. A colossal, patient instrument listening in absolute silence for a whisper from the beginning of time. Generations of ingenuity focused on a single goal to catch a ghost. A relic particle that has journeyed across the entire breadth of space-time untouched and unseen, carrying the secrets of the first second. The challenge is almost incomprehensible, the odds astronomical. But we are a species that thrives on such challenges. We build our temples to knowledge on the precipice of the impossible, driven by a need that is as fundamental as breathing. We need to know what would happen if we succeed. If after all the effort, one of those primordial neutrinos finally ends its long pilgrimage in our detector, what story would it tell? The answer is not merely a new chapter in physics. It would be like discovering the original manuscript of the universe itself, written in a language we are only now beginning to comprehend. The reward for this audacious hunt is nothing less than a new vision of creation. The very first and perhaps most profound revelation would be a moment of stunning cosmic affirmation. For decades, our entire understanding of the early universe, the magnificent architecture of the Big Bang theory, has been built upon a scaffolding of mathematics and indirect evidence. We see the afterglow of creation in the cosmic microwave background, a wall of light from 380,000 years after the beginning. We trace the expansion of space running the cosmic clock backward in our supercomputers. We see the abundance of light elements forged in that primordial furnace. It all points to a single explosive origin. But the cosmic neutrino background is the missing pillar, the direct unimpeachable witness. To finally measure its temperature to confirm that it registers at the predicted 1.95, Kelvin would be to transform theory into tangible reality. It would be the universe whispering back to us, "Yes, you were right. This is how it began." This single number would be more than data. It would be a resounding validation of human intellect, a testament to our ability to piece together the cosmic puzzle from our tiny perch in the cosmos. Imagine seeing the first direct photograph of an atom after a century of only inferring its existence. This would be grander, a confirmation written across the fabric of space-time itself. We would no longer just believe in the Big Bang. We would have held its oldest, coldest remnant in our hands. Yet this confirmation is only the beginning of the story, the cover of the book. Inside, the details are far more tantalizing. The exact character of the CNB, its precise temperature and energy distribution, acts as a cosmic chronometer of unparalleled precision. It would allow us to pinpoint the moment of neutrino decoupling the instant these particles cease to interact with the rest of the universe's primordial soup with an accuracy we can currently only dream of. Right now, our models place this event at roughly 1 second after the Big Bang, but that is an estimate, a superb one, but an estimate nonetheless. A direct measurement from the CNB would be like finding a fossil, not just with the creature's bones, but with a perfect imprint of its last breath. This timestamp is critically important. It would refine the entire timeline of the early universe, recalibrating our understanding of the nuclear reactions that forge the first elements, a process known as Big Bang nucleosynthesis. A slightly earlier or later decoupling would subtly alter the predicted abundances of hydrogen, helium and lithium we see in the universe today. If our measurements of the CNB align perfectly with the observed elemental abundances, our standard model of cosmology would stand stronger than ever. If they differ even slightly, it signals a crack in our understanding, a hint that the universe's first moments were governed by forces or particles we have yet to imagine. The ghost particle would become a cosmic metronome ticking with the precise rhythm of creation's first orchestral downbeat. From this cosmic rhythm we could move to one of the most persistent and frustrating puzzles in modern physics, the absolute mass of the neutrino. For all their abundance, for all their importance, we have never been able to place one on a scale. Our experiments have masterfully revealed that neutrinos have mass, and we have even measured the tiny differences in mass between their 3 known flavors. It is a bizarre state of affairs equivalent to knowing that an elephant weighs 2 tons more than a rhino, and a rhino weighs 1 ton more than a hippo, but having no idea what any of them actually weighs in kilograms. Are they incredibly light or just relatively light? This question has enormous consequences for cosmology. That minuscule mass multiplied by the staggering number of neutrinos in the universe, hundreds of them in every cubic centimetre of space you inhabit, adds up. It contributes to the total mass-energy budget of the cosmos, subtly altering the rate of its expansion, and the way that large-scale structures like galaxies and clusters of galaxies form. The CNB holds the key. These relic neutrinos, though ancient, still exert a faint gravitational pull. Their collective mass would have left a subtle imprint on the structure of the universe as it evolved a signature that could be teased out by comparing a map of the CNB with our maps of the cosmic microwave background and the distribution of galaxies. It's like studying the faint currents in a vast ocean to infer the shape and mass of unseen continents beneath the waves. By measuring these almost imperceptible distortions, we could finally calculate the absolute mass of each neutrino type. It would be a monumental achievement, solving a decades-old mystery and providing a crucial missing parameter that would allow our simulations of cosmic evolution to leap forward in accuracy and predictive power. We would finally know the true weight of a ghost. And it is here, at the edges of our current understanding, that the discovery of the cosmic neutrino background could become truly revolutionary. Our standard models, both of particle physics and cosmology, are stunningly successful, yet they are incomplete. They do not account for dark matter, dark energy, or gravity at the quantum scale. We suspect there is a deeper, richer reality waiting to be discovered. The CNB could be our first glimpse into that new territory. What if when we finally measure it, it doesn't quite match our predictions? What if its total energy density is slightly higher than what the 3 known neutrino flavors would produce? This discrepancy would be world-changing, for it would be the smoking gun for new exotic physics. It could be the definitive evidence for a particle known as the sterile neutrino. This hypothetical 4th type of neutrino would be even more ghostly than its cousins, interacting with other matter only through the force of gravity. It is a phantom's phantom, completely invisible to all our current detectors, but its existence in the early universe would have contributed to the total energy content, and that contribution would be frozen into the CNB like an extra voice in a cosmic choir that we can hear but cannot see. Finding its signature would ignite a revolution, forcing us to rewrite the standard model of particle physics and potentially offering a candidate for the elusive dark matter that holds our galaxies together. The revelations might be even more profound, stretching our very conception of reality. Some of the most advanced speculative theories in physics, such as string theory, propose the existence of extraspatial dimensions beyond the 3 we experience. These dimensions are thought to be curled up compactified on an infinitesimally small scale, completely hidden from our senses. But in the unimaginable heat and density of the Big Bang, their presence might have been felt. Gravity, unlike the other forces, could be free to propagate through these extra dimensions, leaking away from our observable universe. This leakage would have had a tangible effect, subtly altering the expansion rate of the cosmos during its first second of life. A faster or slower expansion would in turn change the precise temperature and energy at which neutrinos decoupled from the primordial plasma. This delicate signature, a watermark of hidden dimensions, would be imprinted forever upon the cosmic neutrino background. To find such a signal would be beyond revolutionary. It would be the first empirical evidence that the universe is vastly larger and stranger than we ever conceived, that our three-dimensional existence is but a slice of a much grander multi-dimensional reality. The CNB would become a periscope, allowing us to peer for the first time into a landscape beyond the known boundaries of space and time. Perhaps the most awe-inspiring prize of all lies even deeper in the past, in a time before the first second before the neutrinos themselves were set free. The current limit to our vision is the cosmic microwave background, that wall of light from 380,000 years post-Big Bang. Before that, the universe was an opaque fog of plasma. We can see no further, but neutrinos can. They can travel to us from just 1 second after the beginning, offering a portal to a far more primordial epoch. And through them, we might just be able to glimpse the universe's violent birth announcement, cosmic inflation. This is the theory that in the first fraction of a nanosecond, the universe underwent a period of hyper-accelerated expansion, swelling from a subatomic size to something vaster than our entire observable cosmos today. This cataclysmic event would have generated colossal ripples in the fabric of space-time itself, gravitational waves. As these primordial gravitational waves propagated through the 1 second-old universe, they would have stretched and compressed the neutrino plasma, creating infinitesimally small variations in its temperature and density. These variations, known as anisotropies, would be frozen into the CNB. They would be the aftershocks of creation. Finding them would be like listening to a recording of the Big Bang itself. It would provide the first direct evidence for inflation, a cornerstone of modern cosmology that has until now remained purely theoretical. It would be a prequel to the first light, a message from a time we never thought we could access, carried to us by the universe's most faithful messengers. Beyond these fundamental revelations, the CNB opens up an entirely new way of observing the cosmos as it is today. It would become a new form of astronomy. For 13.8 billion years, these relic neutrinos have been streaming through the universe, passing through everything. As they journey toward us, their paths are bent and distorted by the gravity of every galaxy, every star, and every clump of dark matter they encounter. This phenomenon, known as gravitational lensing, would subtly alter the patterns we observe in the CNB. By mapping these distortions, we could create an unprecedented chart of all the matter in the universe, both visible and invisible. We could use the CNB as a form of cosmic backlight, illuminating the vast invisible scaffolding of dark matter that dictates the structure of the cosmos. Where the light of the CNB is blocked by gas and dust, neutrinos pass unimpeded. They would give us a new sense, a neutrino vision, capable of perceiving the universe's hidden architecture. It could even reveal unknown interactions. If dark matter particles can on rare occasion annihilate or decay into neutrinos, the CNB would show faint hotspots originating from the dense hearts of galaxies. Or if dark matter can scatter or absorb these low-energy neutrinos, we would see shadows in the background. The ghost particle would become our ultimate probe for the universe's greatest and darkest mystery. When all these pieces are assembled, the true significance of the discovery becomes clear. It is not about collecting numbers or confirming theories. It is about perception. It is about seeing the unseeable. Through the power of computation and visualization, we could translate the data from a successful CNB detector into an image, a map of the sky, not in light, but in primordial neutrinos. This would be the true baby picture of our universe. Forget the toddler portrait of the cosmic microwave background. This would be a sonogram from the first second of existence. We would witness the universe in its absolute infancy, a sea of unimaginably tiny fluctuations in a perfectly smooth ocean of energy. and in those minuscule ripples we would see the seeds of everything that was to come. This tiny variation here, a fraction of a degree colder than its surroundings, would over billions of years blossom under gravity's patient hand into the Andromeda Galaxy. That slightly hotter region over there would eventually collapse to form the Virgo supercluster, the vast cosmic metropolis we now call home. You would be looking at the embryo of the cosmos, the blueprint from which all structure, all complexity and ultimately all life would emerge. It is a humbling, almost terrifying thought to gaze upon the entire history of the universe, not as a story told in retrospect, but as pure, unwritten potential. This single image would contain the legacy of our past and the destiny of our future, encoded in the faint whisper of a particle that has been waiting since the dawn of time to be seen. The detection of the cosmic neutrino background would not simply be an achievement. It would be an act of cosmic archaeology so profound that it would forever change our relationship with the universe and with ourselves. It would be the moment we finally opened our eyes and saw where we truly came from. And so, we arrive here at the very edge of perception. We have journeyed through the quietest laboratories on Earth, standing beside the cryostats and shielded chambers that represent humanity's most audacious listening posts. We have stared into the heart of tritium, witnessing the ghost of a ghost in its decay, grappling with the monumental challenge of isolating one unimaginably faint signal from a universe teeming with noise. The sheer difficulty of the task can feel overwhelming, a confrontation with the absolute limits of our ingenuity. Every particle that isn't a cosmic relic neutrino is contamination. Every vibration, every stray magnetic field, every subtle shift in temperature is a roaring distraction in this search for the ultimate whisper. It is a quest defined not by what is found, but by the perfection of what can be excluded, a process of creating an island of impossible silence in the middle of a chaotic cosmic ocean. This endeavour, this meticulous, painstaking effort to hear a message sent only once 14 billion years ago, is where our story culminates. It is the front line of cosmology, a place where theory, engineering, and sheer human will converge in a singular, magnificent obsession. Our journey to this point has been an epic in itself, a sprawling narrative woven across generations of thinkers. It began not in a laboratory, but in the fertile minds of visionaries who saw the early universe as a cauldron of pure energy. They imagined a time before atoms, before light could travel freely, a primordial state of such ferocity that the entire cosmos was a singular unified entity of unimaginable heat and density. From this theoretical crucible they predicted the existence of two great relics, two fossilized echoes of the creation event. The first, the cosmic microwave background, was a prediction of light, the afterglow of the moment the universe cooled enough for photons to break free and stream across the expanse, an event that occurred a staggering 380,000 years after the Big Bang. Its discovery, a serendipitous hiss in a radio antenna, was a Nobel-winning triumph that transformed cosmology from a realm of speculative philosophy into a precision science. It gave us our first baby picture of the universe, a snapshot of the cosmos as an infant. Yet the theorists knew this was not the first chapter. They knew that an even older story was imprinted on the universe, carried by a far more elusive messenger. They calculated that in the very first second of time, when the universe was a furnace of such intensity that our comprehension falters, neutrinos were forged in colossal numbers. These particles, the most antisocial in the cosmic bestiary, interacted furiously in that dense hot soup. But as the universe expanded and cooled with breathtaking speed, the cosmos became too dilute, too spread out for them to find anything to interact with. At just 1 second of age, they were set free. They decoupled from the rest of creation. This was the true moment of first light, a release not of photons, but of neutrinos. They began a journey through space-time that has continued uninterrupted ever since. This prediction of a cosmic neutrino background, or CNB, was a staggering intellectual leap. It was a prophecy of a fossil far more ancient than the light we could ever hope to see a whisper from a time when the universe was not yet itself. For decades, this remained a beautiful but seemingly untestable theory. The same quality that made these neutrinos perfect cosmic messengers, their profound reluctance to interact with matter, also made them almost impossible to detect. They pass through us, through the Earth, through entire galaxies as if we are nothing more than empty space. They are the ultimate ghosts, To catch one, let alone to isolate the specific ancient low-energy cohort from the Big Bang, seemed a task reserved for a future far more advanced civilization. The challenge was twofold. First, their energy had been stretched and diluted by billions of years of cosmic expansion, leaving them colder and slower than any other neutrino we had ever detected from the Sun or supernovae. They are barely moving, possessing an energy so minuscule it is almost indistinguishable from the quantum jitter of empty space itself. Second, how could you ever build a detector sensitive enough to see such a gentle phantom, while simultaneously shielding it from the constant roaring blizzard of other more energetic particles that bombard our planet every single moment? This is the chasm that modern science is now attempting to cross. The journey from that pure elegant prediction to the colossal technologically dense experiments like Ptolemy is a testament to the relentless spirit of human exploration. It is a story of incremental gains, of brilliant innovations in material science, cryogenics, and data processing. It is a story of quiet confidence of scientists dedicating their entire careers to a goal they may never live to see achieved. They are building the ships for a voyage they may not take, laying the foundations for a discovery that may be made by the next generation. This quest is not for the impatient. It is a slow, methodical construction of a new human sense, an attempt to build a cosmic ear capable of hearing the universe's faintest and most profound vibration. The sheer scale of the engineering is a form of poetry. Vats of ultra-pure materials shielded by layers of ancient lead, and purified water housed deep underground to escape the cosmic rays. Sensors cooled to within a fraction of a degree of absolute zero, where the dance of atoms nearly ceases all to create a pocket of reality, quiet enough to perhaps, just perhaps, register the infinitesimal push of a single ancient neutrino colliding with a single waiting nucleus. It is one of the most exquisite and difficult measurements ever conceived. To succeed is to do something more profound than simply confirm a theory. It is to unlock a completely new window onto existence. Seeing older than light is not just a catchy phrase, it is a literal description of a paradigm shift. The cosmic microwave background. Our previous limit shows us the universe on the cusp of transparency, but it is a wall, a glowing curtain of plasma beyond which our light-based telescopes can never peer. The first 380,000 years are hidden from us forever, opaque to light. All the foundational events that set the stage for everything that followed the epoch of cosmic inflation, the mysterious imbalance of matter and antimatter, the potential birth of dark matter, all of it happened in that darkness behind that wall. The cosmic neutrino background is our only key to that hidden room. These neutrinos streamed directly out of that primordial furnace, carrying with them pristine, uncorrupted information from that critical first second. They are the only direct witnesses. Imagine what we could learn. By measuring their temperature, we could verify the precise thermal history of the universe, as predicted by the Big Bang model, turning a cornerstone of cosmology into an observable fact. By mapping their distribution across the sky, however faint we might find subtle variations, anisotropies that betray the secrets of cosmic inflation, the hypothesized moment of hyperexpansion that smoothed out the universe. These neutrinos would act as a gravitational lens, their paths slightly bent by the cosmic web of dark matter, giving us a new and independent way to map that invisible scaffolding upon which all galaxies are built. We could even potentially search for the mass of the neutrino itself, a fundamental property that has profound implications for the standard model of particle physics and the ultimate fate of the cosmos. Each cosmic neutrino is a tiny encoded message, a carrier of data from an era we have only ever been able to simulate in computers. To read that message would be akin to an archaeologist finding a library that predates the invention of writing a set of records from a time we thought was lost forever to myth and conjecture. It would be the closest we can ever get to placing a probe in the heart of the Big Bang itself. This pursuit, therefore, is about more than filling in the gaps in our cosmological models. It is a deeply human endeavour, an expression of our most fundamental characteristic, the insatiable need to understand our origins. We are a species that looks at the horizon and feels compelled to cross it. We have sailed uncharted oceans, climbed the highest mountains, and journeyed to another world not just for practical gain, but for the sheer soul-affirming act of discovery. The quest for the cosmic neutrino background is the modern manifestation of that same impulse. It is our generation's voyage into the unknown. The ocean is not of water but of time. The mountain is not of rock but of incomprehensible complexity. The new world is not a celestial body but the infant universe itself. This drive pushes us to the very brink of what is possible. It forces us to invent technologies that have applications far beyond the realm of pure science. The hypersensitive detectors, the advanced data filtering algorithms, the mastery over materials at the quantum level, these are the spin-offs of boundless curiosity. They are the collateral beauty of reaching for a goal that seems impossible. In our attempt to understand the beginning of everything, we advance our understanding of everything right here and now. We are compelled to ask these ultimate questions because we are, in a very real sense, creatures of that first second. The laws of physics that were cemented in that initial flash are the same laws that govern the firing of neurons in our brains as we contemplate the question. The slight imbalance of matter over antimatter, forged in that cauldron, is the only reason we exist at all. We are made of the processed ashes of that primordial fire. To look back, to strive to witness that moment, is an act of cosmic self-reflection. It is the universe through us, attempting to comprehend its own birth, and so we wait. We wait in the quiet dark of underground labs sifting through petabytes of data for a signal that may or may not appear in our lifetimes. We refine our instruments, sharpen our theories, and maintain the vigil. The reward is not guaranteed. Nature may have conspired to make this particular secret just beyond our grasp forever. There is no certainty of success, but that uncertainty does not deter us. It fuels us. It is the heart of all true exploration. The value lies not only in the destination, but in the character we build on the journey, the knowledge we accumulate, while striving for something that lies at the very edge of possibility. Every failed attempt, every null result teaches us something new, allowing us to build a better experiment, a quieter chamber, a more perfect trap for these messengers from the dawn of time. What will it be like, that moment when it finally happens, when after years of meticulous calibration and noise reduction, a signal emerges from the data, a subtle statistical preference, an energy signature that cannot be explained by any other source? It will not be a sudden flash or a loud bang. It will likely be a quiet revelation in a darkened control room, a gradual dawning of realization among a small team of physicists that they are the first human beings in history to directly touch the first second of creation. In that moment, the universe will have become a fundamentally different place. A barrier to knowledge that has stood for all of human history will have been torn down. We will have gained a new sense, a new way of seeing the cosmos. And with that new sense will come a flood of new questions, new mysteries we cannot yet even imagine. For every great discovery does not provide an ending. It reveals a dozen new, more tantalizing beginnings. This is the enduring legacy of the quest for the cosmic neutrino background. It is a story of a universe that remembers its own birth, and of a species curious enough to try and listen to the tale. That ancient whisper unleashed in the first heartbeat of time is not lost. It is here now, all around us. It flows through this room, through you, a constant silent river of information, carrying the memory of the fire from which all things were born. It is a fundamental part of our reality, an echo of the ultimate beginning, forever etched into the very fabric of space-time. We are just now, after 14 billion years, finally learning how to listen. And in that listening we find not just the story of the cosmos, but the deepest and most profound story of ourselves. The quest continues. The silence is waiting. And the universe's oldest secret is right here, patiently waiting to be heard.